Let's look at an example of separation of variables applied to a wave equation type problem. So here we are looking at an interval of length L, and we're going to be fixing the position of the vibrating membrane or string at 0 at either end of the membrane. So you can imagine this is like a guitar string from 0 to L where it's bound at either end. And we'll start with the initial condition for the position and initial condition for the velocity of the string. So to go about solving this, we'll make the separation of variables assumption that the solution looks like a function of x times a function of t, and substitute that into the PDE, and we find yg double prime equals c squared y double prime g. And then we divide both sides of this equation by yg c squared, and that leads us to the separated form g double prime over c squared g equals y double prime over y. And again, based on the fact that all of the t variables are on the left and all of the x variables are on the right, we can deduce that these both have to be equal to the same constant value, which we'll call minus lambda. Then at this point, things follow a lot like they did before. So we have a slight difference in that the temporal equation now comes with a second derivative, but the spatial derivative or spatial equation looks exactly as it did before. And so there's going to be the same corresponding three cases. And the boundary conditions that we've chosen, the homogeneous Dirichlet boundary conditions, roll over directly onto the spatial equation for y. And as a consequence, we find, just as before, that it's going to be sine functions that give us our eigenfunctions, and the eigenvalues are going to look exactly the same as before. So we have the same spectrum. And this means that our general solution is going to be the sum from 1 to infinity, and then we'll have some, let's see, alpha n times cosine n pi ct over L plus beta n sine n pi ct over L, and then all of this will be multiplied by sine n pi x over L. So there's our general wave solution. And now evaluating this at t equals 0 for our initial conditions, we have the sum of, let's see, so we've got alpha n, and then cosine of 0 is going to be 1, beta n, and then sine of 0 is going to be 0, sine n pi x over L. And so this becomes a sine series and so we will find those coefficients alpha sub n by constructing the Fourier sine series for capital F. So in other words, alpha n is going to be 2 over L, 0 to L, capital F, sine n pi x over L dx. And then when we go to look at the time derivative for the other initial condition, maybe give myself a little space there, this is going to be, and let's see what happens. So now we're going to have n pi c over L after taking the derivative. And we'll have minus alpha n times a sine, which is evaluated to 0 when its argument is 0, plus beta n times the cosine, which evaluates to 1 when its argument is 0, still sine n pi x over L. And so now what we see is that we get the Fourier sine series for G. From the beta ends. And so these look just like the alphas, except that the integrand has a G in place of an F. All right. So some things to notice about this solution that we have here. Now, in this case, the coefficients of the sine x term are sines and cosines themselves, and in particular, they don't have the decay of the exponential. So, without the e to the minus n pi over L squared kt term, these terms don't decay rapidly with t like we saw before. And so this means that this back of the envelope approximation that we made before of saying that u could be approximated by, you know, just the first term after not too much time, that actually doesn't hold anymore. So, okay, and so coming up soon, we will see different boundary conditions and different corresponding spectrum. When we talk about Sturm-Liouville problems. And that'll be in the next video clip. And so the last two we've seen were both with Dirichlet boundary conditions. So we'll look at Neumann and mixed, like Robin conditions coming up next.